Hey guys, we're going to start off the new year with a little review of the stuff that we've done from this unit so far. We started off at the beginning of this unit with the cathode ray tube. And you remember the cathode ray tube was used by a whole bunch of people, including in 1897 by a guy named J.J. Thomson. And J.J. Thomson used that cathode ray tube to discover the what? The electron, right. And the cathode ray tube looks something like this. You've got an electrode over here on one side. We're going to label this this side is going to be the what? It's going to be the cathode. Somebody said this side over here is going to be the anode. The cathode is going to be that terminal that's connected to the negative side of the power supply. And in the end, we know that it's going to have a bunch of electrons that leave that cathode, travel toward the anode, go right through, and then they hit the screen that glows, which shows us where exactly this beam of electrons hit it. We know that now. We know that it's a beam of electrons that leave the cathode, go toward the anode. But back in Thomson's time, in 1897 and before that, we didn't know that. We knew that there was something mysterious that was leaving the cathode and going toward the anode. We called them cathode rays, this mysterious beam of whatever. But it wasn't until Thomson that we actually determined what these things were. What did Thomson do to determine what they were? Well, he introduced down here, if you remember, a magnetic field. That caused these cathode rays to do what? Deflect, right. And it was observed that these cathode rays deflected, well, if the magnetic field was set up the way that I just have it drawn there, the cathode rays would be deflected downwards. That told Thomson what? If these mysterious cathode rays are deflected downwards in a magnetic field that's pointing into the page, then these cathode rays must be what? Negatively charged particles. Now, we don't know anything about the size of them or the nature of these negatively charged particles other than that they are negatively charged particles. So now he tries to do this little mathematical analysis that we've done a million times back in our magnetism unit. It says FC is equal to Fm, and he says Fc is equal to Fm because they go in a circle. Centripetal force equals magnetic force. mv squared over r equals qvb. He knows what r is. Okay, he knows what r is because he can determine that from where it hits the screen. He knows what b is because he's the one that set up the magnetic field. One of the v's cancels out. That simplifies things a little bit. But he doesn't know what m is, he doesn't know what v is, and he doesn't know what q is. So what does he do now? What does he do now to get something else out of this besides r and b? Yeah, he puts in another magnetic field over here and an electric field over here with two charged plates, a positive plate and a negative plate. We call this the velocity selection chamber, as Paige has said. There's two forces that act here. There's a magnetic force that would act, if we use our hand rule for deflection, magnetic force would act downwards, thumb, fingers, palm acts downwards. The electric force would act upward. Now, for a lot of these particles, the magnetic force might be bigger, or the electric force might be bigger. And if that's the case, then these particles will either deflect up or down. But for the particles that are going at just the right speed, then we know the particles are going to go straight through, undeflected. We're going to select that velocity to go through undeflected. For those particles, we know the electric force acting upwards is equal to the magnetic force acting downwards. Q times E is equal to QVB. Q's cancel. I'm solving for E here. For V. The speed of the particles that go through undeflected is equal to E over B, which gives us another variable here to plug into here. Now we have two variables that we don't know the values of, M and Q. And what we do at that point is just rearrange and solve for the ratio of the two, Q over M. Is this ringing a bell? It's been almost a month since we've done this, eh? Like literally almost a month since we've done this stuff. Found the value of Q over M to be about 1.76 times 10 to the 11 coulombs per kilogram. What was kind of special about that number, 1.76 times 10 to the 11? You guys don't need to memorize what that number is, by the way. If you ever need to know the charge to mass ratio of the electron, then divide the charge by the mass. That's the easiest way to find it, okay? Knowing that is the charge and the mass already. What's special about this charge to mass ratio? Yep. It's really, really big. Yeah, it's bigger than any other charge to mass ratio ever found. That means that if that number is so big, then this number must be so small. And if that number is so small, smaller than any other mass ever found, then it must be a subatomic particle. Okay, if it's smaller than the mass of an atom, then it must be smaller than an atom. It must be subatomic. So these negatively charged particles are now subatomic negatively charged particles that we're going to call electrons. Good? Well, there's the Coles Notes version of the cathode ray tube. Now let's go to the next thing that we did before the break. Talk about the oil drop experiment, the Millikan oil drop experiment. That went a bit of a step further, right? We found the charge to mass ratio of the electron and therefore the discovery of the electron with the cathode ray tube. With the Millikan oil drop experiment, we found the charge of the electron. Set up two parallel plates. One of them becomes positive, one of them becomes negative. In this case, the top plate would be negative and the bottom plate would be positive. We inject these little oil droplets in there. Some of them will be positive, some of them will be negative. Two forces acting on each of them. What are those two forces, by the way? Don't tell me which direction they are, I don't care. Just give me what those two forces are. What's one of them? Force of gravity, good. That's going to act down. Yeah, I won't even ask you that one because that's always acting down. Doesn't matter what the particle is. What's the other force that acts on them? Good, it's the electric force. Now, the electric force on this positive particle acts which way? It acts upwards, right, toward the negative plate. The electric force on this negative particle acts downward. It's away from the negative plate or toward the positive. Now, clearly, this one's going to accelerate, and it's going to accelerate downward. Not only is it going to move downward, it's going to speed up downward. The one on the left, the positive particle, it may accelerate upward if Fe is bigger. It may accelerate downward if Fg is bigger. Or it may be suspended or travel at a constant speed, up or down. Let's focus on this particle right now, traveling at a constant speed. For that particle at a constant speed or suspended, we know that Fe must equal Fg. So Q times E is equal to M times G. And we're going to say Q is equal to mg over E. Now, every once in a while, we have to replace E with delta V over delta D. But most times, this is the equation that we come up with. Solve for the value of Q here. What's it going to be? Give me an example of a value that Q could be here if this experiment produced results that we expect it to produce. What's the value of Q? What could it be? Could be 1.6 times 10 to the minus 19. Good. What's another one? It could be any multiple of 1.6 times 10 to the minus 19. Any whole number multiple, that is. You know, it could be twice that. It could be 13 times that. It could be 16,147 times that. But it can't be 3.5 times that. Okay. That tells us two things. Number one, that there is an elementary charge. And its value is 1.6 times 10 to the minus 19. That's also the charge of the electron. And it tells us as well that charge is quantized. What does that mean? Charge is quantized. Yep. I'm sorry? Yeah, it's got to be, it can only be certain values, right? 1.6 or a whole number multiple of 1.6. What do we do if that particle isn't suspended or isn't traveling at a constant speed? Or what do we do if we're dealing with this particle that's clearly accelerating? Well, in that case, we're going to say F net is equal to the sum of the forces, Fe plus Fg. We're going to say M times A is equal to QE plus m times g. And we're going to solve for the mass. We're not going to solve for the mass. First day back after the break. First period back after the break. First mistake that I've made. There'll probably be more. We're going to solve for the charge here. We're going to solve for the charge. And once we get the charge, we're going to do the same thing as we did with the suspended particle. Look at its value. Recognize that its value is going to be either 1.6 or a whole number multiple of 1.6 times 10 to the minus 19, and then draw the same two conclusions that we drew before. Make sense? Next, we took a look at radioactivity. Radioactivity was a spontaneous process. It was a natural process. Means happens on its own, happens when it wants to happen. We have no control over it whatsoever. It's a spontaneous process. It's a natural process in which the nucleus splits up into something else. It's not stable, it breaks up into something else. Now, there were three types of radioactivity that we dealt with before the break. They were alpha decay, beta decay, although there was two types of beta decay, 0 minus 1 beta, 0 plus 1 beta. And then there was gamma decay, 0, 0. How many protons in an alpha particle? 4, 2 alpha, how many protons is that? Quick. 2. How many neutrons? Good. How many protons in a beta minus particle? Minus 1? How many protons is that? You can't have minus 1 proton, so there's no protons, right? So what does that minus 1 thing mean? It's not a proton, it's an electron. It's an electron. Okay, it's an electron. 0 plus 1 beta, that's not a proton either. That's a positron. Good, the antiparticle of a beta minus particle. And of course, 0, 0 gamma means that it's just electromagnetic radiation. No protons, no electrons, no neutrons, no positrons, nothing. This comes from having, remember we had too many protons. You got two forces that act inside the nucleus. There's this repulsive force that we call the electrostatic force. That's the force that we calculated back in our second unit. F is equal to kq1 q2 over r squared. It can be attractive or repulsive, but in order to be attractive, you either have to have a neutral object attracting a charged object, or positive and negative. And then in the nucleus, you have neutral and you have positive, but it's not a neutral object, it's just neutrons. So you can't have that separation of charge produced, therefore the neutrons aren't attracted to the protons. There's no attractive force between the protons and the neutrons. And there are no negatives in there, so you're not going to get any attractive force as a result of that electrostatic force. It's just repulsive. That repulsive force wants to push these nuclei apart. It wants to cause these nuclei to explode. It wants to cause it to become unstable. But there's also an attractive force called a strong nuclear force that pulls the nucleus together. It acts between these nucleons, these parts of the nucleus, pulls it together. Now, if the attractive force is bigger, then the nucleus is stable. If the repulsive force is bigger, then the nucleus is unstable. If we have too many protons relative to the number of neutrons we have, then we have too big of a repulsive force, and the nucleus will break apart. If the repulsive force is too big, and that's what happens when we get too many protons, then the nucleus breaks apart. If we have too many protons, what do? Well, we break off a chunk of this nucleus and hope that we improve the ratio of protons to neutrons. So this chunk consisting of 2 protons and 2 neutrons breaks off, leaving us with a different nucleus that may be stable or may not be stable, but at least it's closer to being stable. Beta minus decay occurs. Well, this is when we have too many neutrons. What happens then? If we have too many neutrons, that doesn't cause an increase in a repulsive force, but what it does is makes it an energetically unfavorable state. So it doesn't want to stay there. So a neutron changes into a proton and an electron. The proton stays behind, and the electron, which is our beta minus particle, gets kicked out. Remember the nucleus club? We don't want this neutron in there. So we don't want to kick the neutron out because we like him. So we just change them a little bit. We change them into a proton and an electron. The proton stays behind because they're a part of the nucleus club, and the electron gets kicked out. Beta plus occurs, again, when we have too many protons. But something different occurs this time. We don't get this alpha particle breaking off. We get one of these protons changing into a neutron and a positron. The neutron stays behind because they're welcome in the nucleus club, but the positron gets kicked out because it's not welcome. The beta plus particle is the positron. And then finally we have gamma decay, which is just electromagnetic radiation. It occurs when the nucleus is left in an excited state after something else has already happened. When it goes back down to its normal state, EMR is given off. Gamma ray photon is given off. So it's kind of a byproduct of something else happening. And then finally, real quickly, let's just rank the penetrating power and the ionizing potential of these things. Alpha particles have a very low penetrating power. Gamma rays have a very high penetrating power in the range of several centimeters of lead versus an alpha particle, which is maybe a sheet of paper. And then, of course, beta particles are in between, in the middle. A couple centimeters of flesh, 2 or 3 centimeters of flesh, maybe about an inch. The ionizing potential, well, the good news is the gamma rays have a very high penetrating power, but a low, I'm going to put that in quotation marks, a low ionizing potential. Why quotation marks? It's not really low, it's just low relative to the other ones, right? Alpha particles have a very high ionizing potential. And of course, fence sitters, the beta particles, who can't decide where they want to go here. Do we want to have a high penetrating power or a low penetrating power? We're not sure. Let's go in the middle. Do we want to have a high ionizing potential or a low ionizing potential? We're not sure. Let's go in the middle. So these guys are the fence sitters. They're the ones that sit in the middle in terms of penetrating power and ionizing potential. Finally, we did this transmutation thing, this conversion of one element to the other, and these equations that describe the conversion of one element to the other. Again, alpha, beta minus, beta plus, and then gamma, which doesn't change anything really. The big thing we had to remember there is that we had to balance out the number of protons and the number of neutrons. And if we do that, then it's all good to go. Let's say that we have uranium-235 undergoing alpha decay. An alpha particle is 4,2 alpha, and if it's undergoing alpha decay, it's going to appear on the right-hand side because it's being produced, right? This is a parent, we call this a parent nucleus because that's what you start with. And on the right-hand side, we've got the daughter nuclei, what's produced, okay, what's made from the parent. What is made from the parent here? 2 plus what equals 92? I know I'm asking a lot of you right now on Monday morning, right after the break. 2 plus what equals 92? Some people are smiling, meaning, okay, we get it. We know that 2 plus 90 is 92. Some people are just sitting there kind of like, yeah, he is asking a lot of us right after the break. 2 plus 90 is equal to 92. All right. 4 plus what equals 235? 231. And 90, if we look on our periodic table, I believe is thorium. Anything else produced there? No, that's it. That's it. I'm sorry? Yeah, you could. That's right. You could call that 4,2 helium if you wanted to. It's exactly the same thing, but we're not gonna say that anything in addition to that is produced. Okay, we can call it something different if we want, but it's not something else in addition to what we already have there. Let's say now we got. Let's go carbon-12. Carbon-12 undergoes beta minus decay. 0 plus what is equal to 12? Wow, there's a tough one. 0 plus what equals 12? Minus 1 plus what equals 6? This one is a little bit tougher, actually. 7. Be careful with that. If it was a plus 1, then it would be 1 plus 5 equals 6. But it's not. It's a minus 1. Minus 1 plus 7 equals 6. This is going to be nitrogen. Anything else produced there? We could call that an electron if we wanted to. So instead of calling it 0 minus 1 beta, 0 minus 1 electron, but that's not something else. Is there anything else produced there? Good. Plus an anti-neutrino. If this was beta plus decay, it would not be an anti-neutrino. It would be a neutrino. Right? Let's take a quick peek at a couple multiple choice questions. We won't have you respond to these on your phones here. Just do them as a class here. So smoke detectors use a radioactive source, Americanium-243, to ionize the air between two electric plates in a detection chamber. A 9-volt battery causes a continuous current to flow between the plates. When the smoke particles enter the chamber, they neutralize the ionized air molecules, which decreases the current, and of course, that's going to trigger the alarm. If the air is ionized by alpha particles produced by Americanium-243, what's the immediate byproduct that you would expect to find? So we start off with Americanium-243. I think that's AM, isn't it? Americanium-243. It produces alpha particles. The alpha particles produced by Americanium-243. What would we expect to get there? Well, 4 plus what equals 243? 239? The answer's got to be what? The answer's got to be D. Now, if they had been smart when they wrote this question and gave us a couple options that said 239, then how would we determine what it was? We'd have to find the atomic number for americanium on a periodic table, 95, and then we'd say 2 plus 93 gives me 95, and then we'd recognize that 93 is neptunium. We'd check on a periodic table and we'd find that. Okay? Is that good? It's not crazy hard, I don't think. Let's go a step further now. Today we're going to talk not about the reaction per se, but we're going to talk about how quickly the reaction takes place. We're going to talk about a concept called half-life. Half-life is the time that it takes statistically. I'll tell you what I mean by that in just a second. For half of a radioactive sample to decay. If I flip a coin, say I've got 1,000 coins, 1,000 quarters sitting on the desk up here, and they're all on heads. And I flip 1,000 of them. Statistically, how many heads am I going to have left after I've flipped them all one time? 500. Now, is it possible that I could end up with something other than 500 heads after I flip them once? Is it possible that I could end up with 497 and 503? Sure it is, right? Is it possible that I could end up with 200 heads and 800 tails after I flip them all once? Sure. Is it possible that I could end up with 999 heads and 1 tails after I flip them all once? Sure, it's possible. But the further away I get from half, 50-50, then the less statistically probable it becomes. Does that make sense? If you have 2 coins and you flip them over, well, statistically you're going to have 1 head and 1 tail. But you know, with a small sample size, you could end up with easily 2 heads or 2 tails, right? The larger the sample size you get, the more likely statistics are to hold true. The more likely you are to have a 50-50 split there. Half-life is the time that it takes statistically for half of a sample to decay. So if you have a kilogram of radioactive uranium-235, then the half-life is the time that it will take, on average, statistically, to have only a half a kilogram of uranium-235 left. Now that time may vary a little bit because statistics don't always hold true. But if you have a really big sample size, then the statistics usually hold pretty true. Does that make sense? After one half-life, whatever that time is, you may end up with 200 grams of uranium-235 left instead of 500 grams. But odds are, after one half-life, it'll be somewhere around half of it. Statistics don't always hold true. I remember listening to the radio here, I don't know, it was probably 10 years or so ago. I woke up to my alarm and the radio was on, and they were talking about this guy in California that had probably played lotteries, his whole life, and probably spent a fortune on lotteries. I have no idea what he spent on it, but he played 2 lotteries. He played this lottery that his jackpot was, I don't know, however many tens of millions of dollars, and the other one was, the jackpot was like a couple $1 million. He won them both on the same day. He literally won 2 different lottery jackpots on the same day. The odds of that happening, somebody calculated to be something like 1 in a trillion. In other words, statistically, it's never going to happen, right? But it did. Okay? Statistics don't necessarily hold true, but by and large, if we have a big enough sample size, by and large, they do hold true. So statistically, we're going to say that after one half-life, half of my sample is gone. It's changed into something else. But we know that that could vary a little bit. It may not be exactly half after one half-life. Let's take a look at a couple of equations that will describe for us this whole concept of half-life. It'll describe for us how much we may have left after 16 half-lives, or how long it may take to go down to 38% of what we started with. There's 2 equations, and you may recognize these equations if you've taken Math 30. First one, n is equal to n sub 0, 1/2 to the little n. Anybody recognize that one? Anybody seen that one before, or at least something that looks a lot like that before? Yes? Who's in Math 30 right now? Same people that recognize this for the most part, right? We got another one here. N is equal to t over t 1/2. We'll describe what each of these variables mean in just a second here. Math 30 people, what does n mean? Big N, that is. The first variable. Yeah, it's initial amount. The initial amount, the amount that we start with. Can't spell amount. Really, that is a U and an N together, not an M. Because amount, not amount. There we are. Initial amount. Oh, sorry, that's wrong. That's wrong. Paige, I just trusted you. I wasn't even thinking about that. I just trusted you when you told me that was the initial amount, and I just wrote it down blindly. That's not the initial amount. But we can change this really, really easily to make it correct. That's the initial amount. Right, Paige, what is this one? Good. Sorry to mention you by name, Paige, because now the millions of people watching this at home will know you made the mistake. But just so you know, Paige corrected this as well. Paige knew that that was the wrong answer, everyone. This is going to be the final amount. What units are we going to use for the initial and the final amount? Here's the great thing about this. It doesn't matter as long as we're consistent. Maybe it's grams. Maybe it's kilograms. Maybe it's the percent. A percent of a radioactive material that we have. Maybe it's an activity rate. We call it Becquerel, BQ, the amount of decays per second that we have. Doesn't matter what it is, as long as it indicates an amount, and as long as N0 and N agree with each other in terms of the units. What's a little n stand for? No, it's not the time. T stands for time. What does T1/2 stand for? The half-life, yeah. It's the time that it takes for half of it to decay. The units for that can be whatever we want, time and half-life, seconds, days, years, millennia. Can be whatever we want as long as they're the same, right? As long as they're consistent. Is that right? Good. Well, it's the second time through it for you too, right? If you've taken it in math class before. What does little n stand for? Not the time, but rather, yeah, the ratio of time to the half-life, or in other words, the number of half-lives. Good. We've said this a lot of times, right? How do you find a number of something? Divide the total by the amount for one. The total time divided by the time for one half-life. It's the number of half-lives. No units associated with that because it's just a number. Okay. How many fingers do you have? 10. Not 10 something. It's just 10. It's just a number. Okay. So two equations, two relatively straightforward. Maybe not when you see this one being used here. It might not be quite so straightforward. Two equations, one of which appears on your data sheet, one of which doesn't appear on your data sheet, but isn't really that hard to find because you guys know that when you want to find a number of something, you divide the total number of half-lives. It's the total time divided by the time for one half-life. All right, let's take a look at this one on 814. Radon-222 has a half-life of 3.82 days. What's that going to be? N, T, T1/2, big N, little n. It's going to be T1/2, right? That means that if we have a kilogram of radium-222, after 3.82 days, we should expect to see a half of kilogram of radium-222. It may vary by a little bit, but we would expect to see about a half. Now, understand that when we do this, when we say it's about a half, maybe it's a little bit off of that, maybe it's not quite 50%. We're not approximating because we're not smart enough to know anything better. We're not going to say in 5 years, if you've taken a bunch of courses in university in physics, that you can do this any better. You can't. This is a natural, random, spontaneous process. We can't do any better than predict based on statistics. You will never calculate this any better than you are today. Never. Doesn't matter how many physics courses you take. Okay, you'll never know any better than you do today. Okay. It's a big enough sample size, the statistics work. Generally, they work. Question? Yes. It is coming from the computer scientist there who would say that we cannot ever really have a truly random number because you always seed it with something, right? Yeah. This is truly random, yes. What percent of a sample of this isotope would remain after 2 weeks? This is going to be our time, right? This is going to be our time. What percent remains? What are we looking for here? 2 weeks have gone by. The half-life is 3.82 days, which, by the way, is a relatively short half-time, although we can see half-times of less than a second. Still, 3.82 days is relatively short compared to thousands of years that some elements have. What are we looking for here? What percent remains? Forget about the word percent for a second. What remains? What is that? Yeah, the final amount, which is? Looking for n, right? We're looking for n. It doesn't matter if it's percent or grams or whatever. We're looking for the final amount. So we're going to say n is equal to n sub 0 1/2 to the little n. N sub 0, oh, we don't know what that is. What percent remains? Well, what percent do we start with? Almost always. Okay, unless you're given some kind of indication that it's less than 100, then we're going to start with 100%. It's 1/2 to the little n. What's little n? We can find that, right? T over T 1/2. It's, let's say 14 days divided by 3.82 days. 3.666. Now let's pull out our calculators here on the board and make sure that we can do this correctly here. Okay, everybody follow along with this, okay? I want to make sure you can do this correct. Okay, again, if you've taken math class, math 30, then you're going to be pretty familiar with this already. Probably if you haven't, you might not be quite so familiar with it. It's 100 times 0.5, but it's not 0.5 times 10 to the 3.66. It's 0.5 to the 3.66. So we just hit that little hat button there. 7.91. 7.88. Okay, if you use the unrounded numbers here, okay, we should use the unrounded number there. Okay, so what works out to be 665. Okay, so it works out to be 7.88. And what's the units for that? Percent. We start off with 100%, we end up with 7.88%. Now again, we could end up with something slightly different than that, but if we have a big enough sample size, then odds are it's going to be pretty darn close to that. Okay, odds don't always work, right? The odds are not always in your favor, but usually if you have a big enough sample size, we're okay. Good. Let's give these two questions a try at your desk, please. Okay, question just asked about number 2. See, the answer is 75%. And we're asked how much of a 100 milligram sample of tritium remains. We would normally, if we read that question, we would say that N0 is 100 milligrams, right? And therefore, we calculate N to be 75 milligrams, right? That's what they should have had there for the units there as opposed to percent. Now, having said that, that's not an incorrect answer. It is still 75% of what we started with, but works out to be the same number because we started with 100, right? 100 milligrams, 100%. It should really be in milligrams with the way they have the question phrased. Okay, so the number 100 milligrams should be relevant, but they've done it in percent for whatever reason. I think it's just a typo, to be honest. The final answer. Yep, Abby? Yeah, possibly. Yeah, possibly. But if that's the case, don't worry about that. If it makes it easier, actually, Abby, almost. If we have to convert it to a percent. If you didn't hear the question, guys, would we ever have a question like that where we would have to convert it to a percent? Let's say we started off with 1,634 milligrams. How would we do this question if we did have to convert it to a percent? Let's do it in percent right from the top, right? We'd say N0 would not be 1,634. N0 would be 100%. Right? Does that make sense, Abby? Now, alternatively, you could say N0 is 1634, solve for N, and then find what percent N is of 1634, but it would take you a little bit longer to do and be a little bit harder that way. That make sense? Okay, let's do this one. This one that isn't in our book, but you have in the notes that I copied for you before the break. It says the half-life of carbon-14 is 5,730 years. So this is a pretty big one, right? 5,000 years that it takes half of carbon-14 to decay into something else. By the way, when it decays into something else, it's not disappearing, right? If you had a kilogram of carbon-14, you still got a kilogram after 5,000 years. It's just that half of it is carbon-14 and half of it is something else. How long does it take 12.5 kilograms to decay into 400 grams of carbon-14? What's that number? 5,730 years. That's the half-life. That's going to be T1 half. What's this number, 12.5 kilograms? That's the original amount, yeah. Are we allowed to use kilograms for N0? Sure. Kilograms, grams, percent, becquerel, BQ means number of decays per second. Anything we want as long as it indicates an amount. This is going to be N. This is going to be what we finish off with. And we're looking for T here. So let's go this one here. N is equal to Actually, no, looking for t. Let's say this, n is equal to t over t1 half. T is therefore equal to n times t1 half. All right. We know what t1 half is, but we don't know what little n is. Let's go to our other equation to find what little n is. Who wants to rearrange that one for me to solve for a little n? Some of you will have no idea how to rearrange this equation to solve for a little n. Some of you may have an idea if you've done Math 30. How many people have ever heard of a logarithm? 30 people. Isn't that funny? Good news is, if you're not a fan of logarithms or you've never heard of it, there's always a way to do it other than using logarithms. But logarithms can sometimes be a shortcut if you're good at it and if you're comfortable with it. Let's do it both ways. Okay, let's do it the way that some of you that have never heard of logarithms will prefer to do it, and then we'll use logs after that. I call this the divide by 2 method. The divide by 2 method. Okay. We'll make a little table with a little n and a big N. After 0 half-lives, we've got 12.5 kilograms remaining. Right? We have the original amount that remains. After 1 half-life, we've got 6.25 kilograms remaining. After 2 half-lives, we've got 3.125. After 3 half-lives, we've got, let's keep dividing that by 2. 3.125 divided by 2 is 1.5625. After 4 half-lives, we've got 0.78125. After 5 half-lives, we get 0.3906. How many half-lives did it take to decay into 400 grams or 0.4 kilograms? About 5. So we're going to say in this case that n would be equal to 5. 5 times 5,730 years gives me 28,650 years, or 2.86, 2.87 times 10 to the 4 years. Make sense? Now, notice it's not perfect, 0.3905, right? 0.4 is what we really were looking for there. That's okay. Okay, this would be a multiple choice question. You might see an answer that's 2.86. You might see an answer that's 2.87. Okay, whatever way you do it, even if it's not perfect because you use this divide by 2 method, you're going to get the answer. Okay, don't panic about that. It'll be very, very close to an even number of half-lives every time. I'm sorry? Why do I go up to 0.4? Well, 400 grams is 0.4 kilograms, right? So I want to go from 12.5 down to 0.4 kilograms. So I kept dividing by 2 until I get down to 0.4 kilograms, my final amount. And we saw that I had to divide by 2 5 times, so 5 half-lives. All right, now for you logarithm people, let's solve for a little n. N over n sub 0, we're just going to rearrange this equation a little bit. N over n sub 0 is equal to 1/2 to the little n. Now here's the big leap here. N is equal to log n over n sub 0 over log of 1/2. What do we start off with there? 12.5? No, sorry, 0.400 kilograms over 12.5 kilograms over log of 1/2. Let's do that on our calculators now. Guys, if you're not familiar with logarithms, you're not comfortable with this, then don't do this. Okay, use the divide by 2 method. It works every time. It's just a pain in the butt sometimes because sometimes you got to divide by 2, 7 times. But it always works. The logarithm method can be quicker for us sometimes. let's say log, where is it on my calculator here? Right here. Let's say log of 0.4 divided by 12.5. Okay, negative 1.49. Let's divide that by log of 0.5. Right, that's log of a half. Gives me 4.97. What did I find the number of half-lives to be up here? 5. What did I find it to be down here? 4.97, which is more correct, technically. 4.97. But they're close enough together that you're going to get the right answer either way. Okay. Yeah. Absolutely. Yeah, absolutely. Yeah. Absolutely. No, you have to be able to do problems like this, but the curriculum specifically says, word for word, I'll spout off the curriculum objective word for word. It says, perform simple non-logarithmic half-life calculations. In other words, if you ever have to solve for little n, it has to be a whole number. Because the only way you can do that not using logarithms is to do this divide by 2 method. So they have to accept that because they're telling you don't need to know logarithms. But on the other hand, if you do know logarithms, they're not going to take marks off because you use a more correct method. I shouldn't say more correct, a more precise method. Yeah, you'd find this is little n. Okay, whether you find a little n this way or whether you find it this way, it doesn't matter. We're going to take that number and plug it back into here. So it's either 5 times 5730 or 4.97 times 5730. Either way, you're going to get the correct answer, or at least close enough to correct that it would be marked correct on an exam. Yep. No, you never have to worry about that. Is that okay? You guys feel okay with that? Okay. One more tiny little thing with this half-life thing, and then we're done for the day, other than giving you a few questions for homework here. This is a radioactive decay curve. It's a graph. You see the shape of this graph looks something like this. And it's always going to look like that. Doesn't matter what element we have, it's always going to take that same shape. It's never going to be a straight line. It's always going to be an exponential decay like you see right here. N will be on the y-axis, and usually time is on the x-axis. The numbers will be different depending upon what element you have, but always the same shape. There's only really 2 things that we can find from this. The good news is it's not a straight line. That means we don't have to do our analysis of y is equal to mx plus b because it's not a straight line. We're never going to do anything like that. If you go to university and take physics, you may have to actually straighten this line and then use y is equal to mx plus b, but that's for another day. What are we going to have to find from this? Well, we're either going to have to find a time or we're going to have to find an n. If you want to find a time given an n, you're going to go over and down. If you want to find an n given a time, you're going to go up and over. So for instance, what's the half-life of this radioactive element? We start off with 100. After 1 half-life, we're down at 50. Let's go over and down. What's the half-life? 2 years. Done. How much remains after 6 years? Let's go up. Here's 6 years. Let's go up and over. How much remains after 6 years? About 10 grams. So it's either over and down or it's up and over. Nothing else. Does that make sense? Well, that's like the easiest, it's like the hardest graph when you look at it because it's not a straight line, but it's like the easiest graph to actually do what we have to do with it because it's either up and over or over and down. Okay? Yeah, to find time, it's over and down. To find an amount, an n, it's going to be up and over. It has to be one of the 2. So if you try one and it doesn't work out for you, then do the other one. Okay. Here's your homework. Page 817. Some check and reflect questions, page 817. Number 1 to 7. Scratch number 2, guys, sorry. So it's number 1 and 3 to 7.
Lost